Let's try balancing the combustion reaction for the combustion of octane. Now, this one's given to us as a word problem, so we'll have to translate it. So go ahead, pause the video, try to write a balanced chemical reaction for this, and then hit play to see how things went. Okay, let's take a look. Now, the first thing it says is that octane, one of the liquid components of gasoline. So octane, remember that from our nomenclature rules that we use for our covalent molecules, the oct tells us how many carbons are in it. Ane tells us that it's all single bonds. So we'll write that as C8. Then we have hydrogens around that. You may have seen a rule around that you have this number times 2, so 16, plus 2 more, 18. The reason for that is if we draw this as C 1, 2, 3, 4, 5, 6, 7, and 8, and we surround it with hydrogens. You can see that we're going to end up having to add hydrogens in order to get 4 total bonds on each carbon. So these end carbons, you're going to have 1 on each side, plus you'll have an end cap, hydrogen on each. All these ones in the middle, and I won't draw them all in for time's sake, all of these are going to have hydrogens on their sides. So for each of these carbons in the center, they have 2 more. The end ones also have 2 more. So it's going to be the number of carbons times 2, plus that one, and plus that one. That's the idea of that number of carbons times 2 plus 2 rule that you have for linear alkanes. So we'll have this molecule. Now it told me it's a liquid component, so I'll use my cursive L in parentheses to tell me that that's a liquid. So C8H18, liquid phase, can burn, also known as react, with oxygen. We know oxygen, it's going to be O2, and it's going to be gas phase. That's something that we know for sure. This process gives off water vapor, so H2O. When it tells me it's vapor, that means it's going to be gas phase, and carbon dioxide. Carbon dioxide, the di is the number 2. It's not monocarbon dioxide because we don't use the mono for the first word. So that's going to be our covalent or our molecular nomenclature. Now we know carbon dioxide pretty well. I'm breathing out some of it right now. It's a gas. So this is going to be our unbalanced chemical reaction. If you got this far but didn't remember to go further, pause and go ahead and balance out your atoms. Okay, so let's see. We have carbon, hydrogen, and oxygen on this side. I've got 8 right now. I've got 18, and then I've got 2. Over on this side, for carbon, I've got 1. For hydrogen, I've got 2. Then for my oxygens, I've got 3. So you can see this is not even close to being balanced yet. So my strategy is I want to finish with oxygen because that's the easiest one for me to finish off at the end, so long as I have even numbers. Now, I have C8H18, C1O2. So I'm going to have to tweak this. I'm going to need at least 8 of these carbons, right? So let me go ahead and erase this and I'll update my count. I've updated this to be an 8. So right now I've got 8 carbons on this side. I've got 16 plus 1 is 17 oxygens on that side. And I've got 2 hydrogens. Okay, so next thing I need to do is I need to balance up these hydrogens, right? So I have 18 on this side. I've got 2 on this side. Let's go ahead and put a 9 right here and see if that gets me closer. So I'm going to erase these again. I'm up to 9 times 2 is 18 hydrogens. I'm at 9 oxygens plus 16. So 16 plus 9 gives me 25 oxygens. And let's see, then I still have my carbons. I have 8 of the carbons. So things are balanced except for oxygen. Now notice I've got an odd number of oxygens on this side and I've got an even number on this side. So I need to multiply the entire thing by at least 2, right, in order to get everything to be an even number so that I can actually get this to be 50 atoms of carbon. Oh, these things can get big. So I'll put a 2 here, a 2 here, I'll bump this up to be an 18, and I'll bump that up to be a 16. and we'll go ahead and get our counts updated for all of our atoms in the entire thing. So right now I've got carbon. I have 2 times 8 gives me 16 carbons, and I have no others, so 16 carbons. I have 18 hydrogens times 2. Let's see, so that'd be 9 times 2, that'd be 9 times 4, so 36 hydrogens. And then oxygen, I've got 4 at the moment. Obviously, I've got to tweak that one here in just a minute. Now I'm going to come over to this side. I've got 18 times 2. That'll give me 36 hydrogens and no others, so 36. I go to the oxygen. I've got 18, plus I've got 16 times 2. So that'd be what, 32. So 32 plus 18. So 32 plus 18 gives me 50 total oxygens, just like I had before. And then I checked my carbons. I've got 16, and I've only got 1 inside the atom and the molecule, so I've got 16 there as well. So now we can see that I can finish this one off. I need to have, let's see, 46 more of these atoms in order to get there. If I do that by 2, so that it fits the stoichiometry within, I'll have to do another 23 plus 2, so 25 O2s. I'll go ahead and erase that. That'll get me my 50 oxygens that I need to have there. You can see now that I have a balanced chemical equation. Now, that was a long road, and that sure is a bunch of large stoichiometries. Let's check to see if we can reduce it at all. I've got an even number, even and an even, but we have an odd there, so I can't reduce it by the factor of 2. I see a 5 here. I can't reduce by a factor of 5, 8s or 9s. So no, that's going to be the smallest ratio I can have between those molecules. Now just to emphasize what that's going to look like, we're going to have our octane molecule plus oxygen yields carbon dioxide and water, but we're going to have a lot of these. 2 octane molecules and a bunch of oxygens, 25 to be exact, are going to yield 16 carbon dioxides and my 18 waters. That's our combustion of octane.